Hi, my name is Amelia. I'm a senior on Team 328, the Aluminum Narwhals, and today we're going to be talking about energy and work and power.
All right, so we're gonna talk a little bit about how all of those things relate to the ideas of motion and forces, which we talked about in the past couple weeks. So when you're thinking about work, essentially what it means is just when you're moving something by applying a force. When we're talking about mechanical motion, that's basically how you can think of it. And these aren't official definitions; they're just kind of to give you the general concept of what all these things are. And so energy, or how we relate that to work at least, is when you do work on an object, that's the same thing as transferring energy, because work can be defined as the change in energy of an object. And then power is another kind of concept that relates work to the amount of time that you do work in. So you think like you have a lot of power, you can, that's the same as getting a lot of work done in a short period of time. And we'll show you that kind of mathematically in a little bit. But work or power can essentially be defined as the rate at which you do work. So some examples of work can be things like anything that causes an object to move in this sense. So that can be things like pushing a box or throwing a ball. And all of those things require energy, and you can also measure the power that you use when you're doing that work. All right, so let's look at it a little bit more mathematically when we're talking about work. The basic equation for work is force times distance. So, and like I said, that's also equal to the change in energy. We got a little delta here. In case you didn't know, delta, that is that little triangle symbol. It just means the change in energy. Like I said, work is when you move a thing by applying force. So this equation just relates how much force you do over the total displacement of the object that resulted because of applying that force. So since force equals mass times acceleration, like last week, you can remember that the units of force are newtons, right? Which is the same as kilograms times meters per second squared, excuse me. Right, and then so that's force. But then when you're looking at displacement, or the distance that you cause the object to travel, that's just, we'll just use meters for that. So then looking at this, we can kind of figure out what the units of work would be. So if you just multiply newtons times meters, you get this unit called Newton meters, and that's literally just Newton times meters. And so you can work out, that also equals, if you wanted to find that in terms of kilograms, meters, and seconds, you could do that, but generally we just look at Newton meters. There's something that also is used to measure work, and might be a little more common than Newton meters depending on what you're doing. It's called a Joule, and a Joule is basically just 1 Newton meter, and that can be represented as just a J. So let's kind of use this equation to do like a little quick example problem here. So let's say you have, you're trying to move a refrigerator across your kitchen just through pushing it horizontally. And you do this by applying 200 newtons of force applied across 2 meters. So how would you find the work that you performed on this refrigerator? Well, using the equation work equals force times distance, that's just 200 newtons times 2 meters. And that is equal to 400 Newton meters, or 400 joules. So something else that you have to keep in mind when we're talking about work is that the direction that you apply force matters. So let's say here's your box and you're trying to move it, or your refrigerator or whatever, and you're trying to move it across this floor. If you want to use the equation work equals force times distance, you could only look at the amount of force that's being applied in the same direction as the displacement that you're interested in. So let's say you push it straight this way, and that's 200 newtons. That should be a little arrow, more or less. So that's 200 newtons, and then you would just want to look at the total displacement of that. But what if you applied like 200 newtons like up at kind of a funky angle? Well, you would still be applying that same amount of force, but the direction that you're applying that force in ends up not all of that force ends up moving the box to where you want it to be. So and this gets a little bit complicated when we're talking about trigonometry. Well, it's not that complicated, but it's something that we're going to go into today. So just kind of a little takeaway from that is that you only want to use this equation when your force is in the same direction as is the same direction to your displacement. Okay, so let's talk about power. So power is the rate at which you do work, right? So the rate involves how much time you take to do something. So equation-wise, power equals work divided by time. So we can look at the units of this again, right? So if work is in terms of joules or newton meters, and you divide that by seconds in time, that'll just equal a unit called a watt, which is often represented by just a capital W. And also, if you're just relating this back to energy again, if you remember, work is also the change in energy. So you can also say, where's some space for a delta, is the change in energy over time. Or power is the change in energy over time, excuse me. When you're doing things fast, that's more power and less time. But if you're doing things slow, that'll be less power and more time. And that makes sense if you look at the equation, right? Because if you increase time here, that fraction of work over time, if you have a higher denominator, which means slower, that's going to decrease your total value for power. And then if you have less time, that's going to be more power because that fraction is going to be higher if you have a smaller denominator. So going back to kind of our fridge example, let's say, when you had 200 newtons of force across 2 meters, so that was 400 joules of work, right? But say you did that in like 5 seconds. What would be the power? So we would just plug that into that equation here, right? And you already solved for work earlier. 400 joules, right? The work divided by 5 seconds in time, because we're using all in seconds here. And that just equals 80 joules per second, might be your initial thought, and that would be also correct, but that ends up working out to also be watts. So all these units can kind of be converted to one another depending on what you're working with. Didn't say 80 joules or 80 watts. All right, so that's kind of a super basic overview of force and power. So now let's get a little bit more into energy, which relates to the activity that we have this week. And energy, you think of, it's just, how much energy you have to do something. So like you wake up, you have a lot of energy in the morning, or you don't have a lot of energy in the morning to do whatever stuff you want to do during the day. And there are several different types of energy. Some of them, mechanical energy, which is just like the moving things, sound, light, heat. There's a whole bunch of different types of energy, but all of those can kind of be broken down into 2 main types of energy, and that's potential energy and kinetic energy. So when we're talking about kinetic energy, that's just the energy of motion, energy of moving things. So kinetic energy can also be converted to potential energy and vice versa. Kind of a key concept when we're talking about energy is that energy is conserved, or just conservation of energy. So that means however much potential energy you have will end up being however much kinetic energy you have, as long as you're not losing energy through some other way, like friction or something. So let's talk about this as an example. So let's say you have a ball rolling down a hill, or I guess that's more of a purple triangle than a hill, and you can measure its potential energy and its kinetic energy. But let's say it's starting off at just at the top of this hill. It's not moving, it's just kind of sitting there. And it's at a height of, let's call that h. And it has a mass of m. So that'll be in like kilograms, and height would be in like meters. So if we want to put an equation to it, potential energy, or in this case gravitational potential energy, is represented by mass times g, or gravity, or the acceleration due to gravity, times height. So this is for gravitational potential energy. There are different types of potential energy. I'll give you some examples later. But this, when you're talking about gravitational potential energy, it can also be represented as just a capital U. So if we wanted to find the potential energy of this ball here, that would just be the mass of the ball, which let's say the mass is equal to 1 kilogram. And then let's say the height, let's say that's like 5 meters up. So the potential energy here would be mass, or 1 kilogram, times gravity, or the acceleration due to gravity, which on Earth is about 9.8 meters per second squared. That's just kind of a constant for Earth, Earth's gravity. And then height would be 5 meters. It's the same units as work, which is joules. Because if you remember, work, right, is the change in energy. So that equals 49 joules, which, and again, a joule, remember, is kilograms times meters squared per second squared. What would happen if we push this ball and it started to roll down the hill? Just like we calculated potential energy, we can also calculate kinetic energy. However, if you remember that energy is conserved, in this system, let's say, like there's no friction and no other outside forces happening, so that would mean all of your potential energy is completely converted to kinetic energy. So if you had 49 joules of potential energy, you would have 49 joules of kinetic energy. The equation for kinetic energy is 1/2 times the mass times velocity squared. So let's say, like if you wanted to calculate how fast the ball was going, or the velocity, you could calculate that because you already know the total potential energy, which equals the kinetic energy. And you also know the mass of the ball. So that means 49 joules equals 1/2 mass times velocity squared. Since you know the mass is 1 kilogram times your velocity squared, so you can just do a little bit more calculations here. 49 divided by 1/2 is 98. Since you have joules divided by kilograms equals your velocity squared. And that just velocity, remember, is meters per second. And then also joules divided by kilograms equals meters squared per second squared. So then if you just take the square root of 98, so your velocity would be 9.9 meters per second. So something important to note is that this is the velocity of the ball only when it's at the very bottom of this slope, because if it was at any other point during the slope, it would still have some potential energy here, right? Say it was like here and it was at, 2.5 meters of height, it would still have half of that potential energy that it had, and it would only have, and then half of the energy would also be kinetic energy. So this is only, this equation here, or this calculations, is the velocity of the ball at the very bottom of the slope. So some other examples of potential energy that can also be translated to kinetic energy are things like rubber bands, like in the activity this week. So if you have, say, a rubber band and that's stretched back, and the rubber band is stretched back, you stored some energy in that rubber band as potential energy. Once you let it go, all that the energy that was once potential energy goes into propelling the rubber band forward, or something that it hits forward. So another example of like elastic potential energy would be, say you have like a bow and arrow. Oh, that's a bad drawing. But say you have like a bow, and its string is pulled all the way back. So say you have all that potential energy stored in the string. Once you let that go, and as that bow kind of flexes kind of back into its natural state, and the string is just kind of chilling, it doesn't have any potential energy in it, all of that potential energy that was stored in the string and in the bow is now propelled into kinetic energy in your arrow, which is now off me. All right, so that's kind of the basics of potential energy, kinetic energy, and work and power. Remember that we're also going to be going over this in the live stream this Friday at 3 p.m. To kind of go over any questions and maybe some practice problems.